So I've started the recording and we'll share the recording with you after the session. So today we'll do the revision for week 5 and 6, and tomorrow we'll do for week 7, 8. And again, you have one more session with Prof on Saturday. So there you will cover again the linear algebra part. So let's get started. All right. So as you know, in week 5 we start with the complex numbers, right? So let's do some very basic problems. Start from basic problem. So first, let's do this problem where x belongs to C3 basically and y belongs to C3. You have two vectors in complex plane, and you have to find what is x plus y and what is so if I let's say if I take x plus y to be z, then what is your z bar?
Do we need to solve it?
Yes, you need to solve it. Will this slide be shared? Yes, the slides will be shared after. Tomorrow morning we'll share it.
And ma'am, where will you put them? On the dashboard?
On the dashboard, yes.
In supplementary contents?
Supplementary content, yes. No,
ma'am,
this is...
one more question I want to ask is there a quick way to find the eigenvectors when we know the eigenvalues?
It's the same way you do the null space of A minus lambda I.
Yeah. Any other way, ma'am?
No, like that's the way you find the eigenvectors. Okay, so
I'm done.
Yeah, it was quite easy. So what is the sum? What is x plus y?
We have to give the answers, ma'am, actually.
You can put it in the chat box. Okay. So this is quite easy. I'll just go through it. So x plus y will be just
Ma'am, it
one.
will be 1 plus 2 iota.
2i.
Yes, right.
3 and minus 4 minus 5 iota.
3 plus 0i. We have to write in that way, no, ma'am.
So z will be, it will be 1 plus 2i, 3 and minus 4 minus 5i, right?
Yes,
ma'am.
Now if I want z bar, so what is z bar?
1 minus 2i.
1 minus 2, conjugate of the complex set.
For conjugate, we have to...
1 minus 2i. What should be the next one?
3, just 3.
Just 3, right?
3.
Then it is minus 4.
Minus 4 plus...
Is it not necessary to write plus 0i?
No, not necessary.
Complex part, no need, ma'am?
No need.
Okay.
Yeah. Okay. Let's do the second one. So, like when you are in real vector space, there the dot product is just the element wise multiplication, right? But in case of the complex vector space, that is not the case. How do we define the inner? In the case of the real vector space, our inner product was defined as like x transpose y, but we cannot do the same when we are in complex space, right? So in this case, our inner product is defined as something like x bar transpose y. So again, you have the same matrix. Can you find the x dot y in this case? So you can again put your answer in the chat box.
Ma'am, will this recording be shared?
Yes, the recording will be shared. Like, I'm not able to live stream this, it is not scheduled. So I will
Yeah.
put the recording along with the slides tomorrow morning.
Okay. And it's on the portal, right? You'll share it
It
on the
will
portal.
be on the portal. Yes.
All right. Thanks.
Ma'am, I think it was scheduled because I got a YouTube notification. Like
Uh,
starts in 30 minutes.
yes, yes. I mean, but here in this case, like, I'm
Okay.
not able to like live stream from here.
Okay, okay.
Yeah, yeah. Let's find the inner product. Okay, somebody got -6. -29 -9i. Okay, I have three answers here.
Ma'am, can you once show the multiplication of the complex numbers?
Multiplication of the complex number. Okay, 3 more minutes. Okay, so I see there are various answers here. If the majority is -19 plus 39, that's the right answer. Okay. Do you need more time, or should I go ahead with the solution?
Just 2 minutes, ma'am.
Okay, all right. Should I proceed now?
Yes, ma'am. You should proceed.
Okay. All right. So we had to find x bar transpose y, right? You had x to be this and y to be this. So our inner product, that is x dot y, is x bar transpose y. Okay. So let's do what is x bar. So x bar is 3 minus, sorry. Right here. So x bar is, what is x bar? Can someone tell me?
Yes, ma'am. 3 minus 2i.
Minus
No,
2y
3 plus 2i.
Plus 2i.
3 plus 2i.
Minus 2 minus I.
Correct.
Minus 4 plus 3i.
Right.
Ma'am, everybody's voice is echoing. Have you logged in two devices?
No, I have not logged in through two devices. Is somebody recording it? Something?
When we speak, we hear our own voice. Once again.
Is it is everyone hearing the
No,
two
ma'am.
devices?
No,
No,
ma'am.
it is not
No,
It's
visible.
ma'am.
fine. I think
I
it's
could not
Someone is on
hear
speaker.
problem
myself.
from his side.
I one reason can be somebody is already recording it, and if the mic is on, it may come. So
Yeah, even
please
speaker is
keep
on.
yourself muted. Yeah.
What's the answer, ma'am?
It's fine, ma'am. Continue, please.
Okay. So x bar is this. Now you do x bar transpose. So x bar transpose y, right? So you have 3 plus 2i minus 2 minus I minus 4 plus 3i. Then you have y. What is y? Minus 2 plus 4i
5 minus I
5 minus I
minus 2i.
minus 2i, right? Now you do the product. So you get 3 plus 2i minus 2 plus 4i. Then you have minus 2 plus
Minus 2.
yeah, minus 2 plus I, 5 minus I plus minus 4 plus 3i.
Minus 2
2i.
minus I, ma'am. Second term is minus 2 minus I.
All right. Like I have written 2 plus
Ma'am,
2.
there,
Susmita,
but then here
you
also
are
you have
logged in
changed.
two devices. Yeah, please mute. Susmita Mande.
Ma'am, here then you have to change. No? If you are giving minus in
Sorry,
the
I did not understand.
minus 4 plus 3i, you are taking minus outside, right?
This is minus 2i, no?
Not there, ma'am. Here, minus 4 plus 3i.
Minus 4 plus 3i, yes.
It should be 4 minus 3i.
Yeah, it should be 4 minus 3i because you are taking minus outside.
It's
Or you should take a plus
minus of
No,
outside.
no, I'm not taking minus outside. So what I've done is like this is minus 4 plus 3i. Instead of writing minus 2i, I took this minus here. Got it?
Ma'am, it's correct.
Yeah. So let's multiply. Now what do you get? So 3 2 minus 6. So 3 12i. Then you have minus 4i plus 8i square, right? Then minus you have 10 minus 2i plus 5i minus I
I
square.
square you forget to write, man. 8i square.
Oh, sorry. Yeah. Then minus, sorry, this is 8i. Then minus I square, 6i square, right? What do you get? You get minus 6 plus minus 6 minus 8. Then you have plus 8i from here, right? Then you have I square minus 1, so 11 plus 3i plus 8i 6i square minus 1 plus 7, right? So minus 14
Plus.
minus
It's
11 plus 7. Yes.
It will be plus 6, right? At the end.
Plus 6, ma'am, not 7. I square is minus 1. No?
Did I add this from some plus 1 from somewhere? Wait.
No.
The last term,
No?
7.
No.
Okay. Okay, thank you. Okay. So this is 6.
Ma'am, from where did you got minus 6i square?
This is from minus 2i plus 3i. So minus
Okay,
6i
okay, I
square.
got it.
Yeah. This is fine. Now you have 8i plus 3i. 16, 17, 18, 19, 19i. So you get 19i. Sorry, it is minus, no. 16 minus 3. 16 minus 3 is 13i. And this will become, this is minus 24 minus 25 minus
1.
25 plus 6, which is minus 19. So you get the answer to be 39 minus 19.
Ma'am, we shouldn't write like I is equal to 1. So
I equal 1.
minus 9 minus 19 plus 13 is equal to 6
No,
minus
no, I is not 1, no.
I mean root minus 1.
I square is minus 1.
I square is minus 1.
Okay.
So this, if you want to write it in the form of a plus iota b, you can write this as minus 19 plus
Okay,
iota
this is
13.
understood. Okay, ma'am.
Yeah.
Ma'am, can you explain the thing you written on the last second step?
This one. This one.
Which one I can't see?
No. Which step do you want me to explain?
Last second step.
Second last, this one. Or this
Yes,
one.
ma'am.
This one.
Yes, ma'am. Yes, ma'am.
So I have just done the calculation. You can just check it. So I have taken. So this is minus 6, minus 8.
Minus 8i, right? That will be plus 8i plus 8i.
Minus 8, right? Minus 6, minus 8. So minus 6, minus 8.
No, ma'am. From above, like it's plus 12i minus 4i, right? That will be
Correct.
plus 8i.
Plus 8i. I have got it. So this is minus 6. From here, minus 8 is
Okay,
coming.
okay. So you
And
written
from here, 8 is
okay,
coming.
okay, okay. So you had swapped that value. Okay, I got it.
Got it.
Okay, I'm
Okay.
confusing that.
So this is your answer. All right. Let's move to the next one. So you have this matrix A. Now you have to find the length of the column vector. So just be careful. This is in the bracket, okay? Just find the length of the column vector. So if I'm saying length of the column vector, so if let's say this is C1, this is C2, then find what is the length of this vector, what is the length of this vector.
I suppose it would be easy to do. That is the x conjugate transpose into x.
X yes, that is how you have to do, no?
Can we go to next question?
Ma'am, we have to find length for both the columns separately or just
separately.
Okay.
Ma'am, YouTube streaming is not going on, ma'am.
Yes, YouTube streaming is not going on. I'm recording the session, so we'll upload.
Okay.
Ma'am, please upload the slides also.
We will upload. So
And this is a revision for quiz 2, right, ma'am?
This is revision for quiz 2. Yes.
Okay. How many weeks it will be covered today?
Or 2 weeks.
5 and 6.
Yes.
SV.
Yes.
Ma'am, can you tell us the weightage which would we be getting from week 5 to 8?
Weightage will be almost same for all the weeks. Maybe a little less for week 8, but
Ma'am, are we
remaining 2
getting
weeks it will be almost
3
same.
cross 3 matrix?
3 cross 3 matrix for
SVD, SVDs, and like most of the things, yeah. We find difficulty to find the eigenvalue of 3 cross 3 mostly.
okay.
So you told that you will not get.
It might come, but if it is coming, no, it will be very straightforward. It might come, okay, but it will be very straightforward. You won't have to worry much about the calculation.
C1 is 1.
Okay.
Both is 1, ma'am. Both are 1.
Both are 1, right? So one more thing I wanted to check. So can you check if these two vectors are orthogonal?
Yes.
It is orthogonal?
No.
I'm getting 0, madam. 0.
I am also getting 0 for
Yes,
both.
sir. I'm getting 1 and 0, ma'am.
No,
1
I'm
and
getting
0.
both 0.
How are you getting 0 for which one you are getting 0?
I'm getting for both 1.
For both one you are getting 0. Okay, how?
You can never get 0 norm. You can only get 0 norm if the vector itself is 0.
Vector itself is a 0,
Exactly,
right?
right.
So
You have
see,
to-
these are like, even if you do the these things will come, like these basic things you'll have to keep doing it for like if you have a unitary matrix, you will have to find the length. So you should know how to find the length of a vector.
This is how we take C1, column C1, which has 1 by root 2, I by root 2.
Hmm.
So how do we just do the Euclidean, or I mean, I didn't get it. I'm getting 1 and 0. How to do it? Can you get it?
Okay, so how many of you have got 1?
Yes, ma'am. For both it is 1.
No, for C1 I got 1,
Both
but
it is
C2
1.
I am not getting.
Okay.
I mean, actually, what do we square each of these and add up? How?
All right. Let's do this. So let's take your z1 to be 1 by root 2, okay, and I by root 2. Now we need to find what is the length of this vector. So length is nothing but the norm, right? So how do you give the norm? So norm is, so this norm is given by, so it will be basically z1 bar transpose z1, right?
Basically, it is norm square, no?
Norm square.
Yeah. If we get some other value other than 1, then we have to take under root for the length.
No. What did you say?
If we get, suppose if we get 4, then the length of the vector will be 2, no?
Length of the
That's
vector will be 2. Yes.
Yes. And norm is that is square only. Norm
Yes.
is the length only, no, ma'am?
Norm is the length only. So now z1 bar transpose is what? Again, it's the same thing. We did it previously, right? So what is z1 bar transpose? It is 1 by root 2 minus I by root 2. And what is z1? 1 by root 2 I by root 2, right? So you get 1 by 2 plus minus I square by 2, which is 1 by 2. This gives you 1, right? You should know always how to find the
Ma'am,
length of a vector in complex
ma'am, like
space.
I have a confusion in when to do this norm square or direct norm, only norm.
I mean, you have to, if you have to find the length, you do norm only, but you will have to do under root. Here I have just, like after this, I can just do norm of Z1 and I will say it is 1. That's all. Okay.
I mean, the 1 is under root 1, so it is 1.
Yes, yes.
Okay.
Now, similarly, you find it for Z2. So it will be what? Z2 bar transpose Z2, correct? So this will give you 1 minus I by 2, 1 plus I by 2, right? And then you have 1 plus I by 2, 1 minus I by 2. All right. So what will you get? You will get 1 minus I by 2, 1 plus I by 2, right? Plus 1 plus I by 2, 1 minus I by 2. Okay. Now, what is what will you get after this? So this is 1 minus I, 1 plus I. So you can do a square minus b square.
So it will be 2 by
Is it 2, ma'am? Is it 2 or is it root 2? I think it's root 2.
No, it is 2, it is 2, right? It is 2.
Okay, okay.
Okay. And then again it is 1 minus I square by 4. Sorry, 4. So what do you get?
1. 2 by 4 plus 2 by 4, which is 1.
Yeah. So do not get confused with the real vector space and the vector complex vector space. So the length is defined in a different way when you have the complex vector space, and you should know how to find the length, because if you have to, let's say, find the like unitary diagonalizable matrix for A, then in that case you need to know how to calculate the length for a complex vector. So do not get confused. Now again, if you have to check for if these vectors are orthogonal, then what do? You do A dot B should be 0, right? So again you can check.
Element wise multiplication.
So
But
you need
before
to
that,
check.
we have to do conjugate.
Element
No?
wise orthogonal as well. Okay.
Yes.
X transpose, X bar transpose Y is
Yeah,
equal to 0.
Z1 conjugate of transpose.
It is 0.
It will come out to be 0. Just check. So do the same thing. It will come out to be 0. So they are orthogonal also. Okay.
So we need to direct multiply them or just do conjugate of them?
No. Again, they are complex, right? So you'll have to do the conjugate.
Okay.
You cannot directly multiply.
So conjugate would be Z bar transpose then Z2.
So you will get 1 by root 2 minus I by root 2 and multiply it with 1 plus I by 2 and 1 minus I by 2.
Ma'am, is it sufficient to just check Z1, Z2, or do we have to check Z2, Z1 as well? Because the multiplication is not commutative, right?
Multiplication is not commutative.
I mean, like X dot Y is not Y dot X.
Yes, it is not.
So does that mean we have to check for orthogonality?
No. You just check for X dot Y when it is enough.
So does that mean if X dot Y is 0, then Y dot X will always be 0?
Doesn't happen in this case, right? In complex vector space.
I didn't get.
I mean, X dot Y is not equal to Y dot X.
No, it will happen, ma'am.
That I got, but I'm just asking. So is it sufficient to just check X dot Y for orthogonality, or do we have to check both X dot Y and Y dot X?
I think, ma'am, any two vectors, if a product is 0, then other way is also 0. Because both are perpendicular, right?
In case of perpendicular vectors, like this will happen, but in general, it is
In
not
general,
true.
yes, ma'am. Only in
In
case of
general, it is
orthogonal, it
not
will happen.
true.
Okay.
Here, when we're discussing this perpendicular thing, actually I have a basic doubt, ma'am. So in the tutorial, actually, like when we started with complex numbers, Sir was mentioning that let's say you have a complex number. So how do you represent it in the? Can we just?
Can
I'll
you
give you
tell
the
me
times.
which?
Yes,
Yeah,
ma'am.
can you give me
Timestamp.
the
Yes, ma'am.
timestamp?
Yeah, timestamp. I'll just one second. Timestamp is tutorial 5.1. Timestamp would be around 5 minutes. Yeah.
5 minutes. Okay. Let me check.
Tutorial 5.1. Because once that becomes clear in terms of representing in 2 dimension or whatever, um, then things will become much clearer. I thought. T. I have it open. Can I share now? Is it possible?
You told 5 minutes, right?
Timestamp 5 minutes.
5 minutes. I'm seeing over there. What now do you have?
Okay, I'm not able to. We are not able to see your screen.
Okay, wait. This one.
Real axis, real and it's or Hermitian symmetric matrix. You can talk about all properties or types of complex matrices. But the question is this whether the
Ma'am,
elements
it's gone
in this
quite ahead. Can
matrix
you come
are
back to 5?
random?
I think
I
it's
just
already
inserted
crossed
all those
7.
elements because it should be a
Back.
complex matrix or see,
Yes, ma'am.
right?
Here.
So
Here.
the
So
reason is
sir
if
was
I want
saying, can you
to
pass this here?
plot the other element, I need see.
So here,
that is one skill that we should have.
for
Apart from
representing.
visualizing things,
Can you pass it,
we
ma'am?
should be comfortable with.
Pause it. Okay, okay.
Yeah. So what I was like wanting to clarify was here for the example that he's given, like let's say the vector x is 1 plus I and 7th earth is 1. So I was saying that for representing this, unlike in the case of real numbers, like here in 2D, like x-axis will be the real part, y will be the imaginary. So and we were saying that we can represent one unit along real axis on one. And the next example was like taking another vector, and he said that if we have another vector, we cannot represent here. So I was thinking for let's say you have a negative part, like for example 1 minus I or any other. So the negative y-axis can also be taken as an imaginary part. No, when the imaginary part is
Yes,
negative.
yes. So one thing I want to just tell here. So there was some notes from week 5 that was circulated on discourse. Did you get it?
No. Notes on week 2. Is
Notes
it
on
available?
week 5.
Sorry, week
Our
5.
instructor Karthik had shared few notes.
It has sent Through
No,
mail.
ma'am, I don't have it, ma'am.
So
Yes,
through mail
ma'am.
you have gotten it, right?
Through mail.
Yes,
No,
ma'am.
Okay.
mail.
The
We
mail
don't
we
receive
got.
any mail.
So mail,
Yes.
I'm not checking on a regular basis. So quite like not in.
Okay, so
Can
one
someone tell
thing,
me the
yeah, if
date of
someone
that?
is has it with you, you can please share it here. So what I would suggest is like for week 5, it's a very good notes. You can go through each of the points that is discussed in the lectures, like a summary of whole week 5. It's very neat and very precise. It's very well written. So please go for revision if you want. Please go and just have a look. Okay.
Okay. Thank you very much,
Yeah,
ma'am.
even on discourse it is there, so you can take it from there also if you want.
Yes,
Ma'am,
ma'am.
did you remember how we can find in this course? What is the topic for it?
Topic I don't remember.
Okay, okay.
Yeah. All right, let's go ahead. Okay, so now we have from the Hermitian matrices. So when do we call a matrix to be Hermitian?
A star is equal to A.
So Hermitian matrices, right? So you call a matrix to be Hermitian if A star comes out to be A, right? And what is A star?
A conjugate transpose.
Conjugate transpose.
A conjugate transpose. Okay. So on this line, you will have to choose which among the following matrices are Hermitian. So you have 3 matrices here. Can you select which one are Hermitian and which one are not Hermitian?
First one is a Hermitian.
Okay.
The rest both are not done.
C also, ma'am. Oh, no, no, no. So sorry. No, no. C.
Only A is Hermitian.
A only, ma'am.
Only A is Hermitian, right?
Yes, ma'am.
So you see this A 3 minus 3i will become 3 plus 3i, right? So this is Hermitian. Again 3 plus 3i, same as 3 plus 3i, so it is not Hermitian. And this is 3 plus 3i, and you have 3 minus
Ma'am,
3i.
the diagonal elements are
diagonal
not real, so it is not.
Right, yes, the diagonal elements are not real in this case, so it is not Hermitian. So it is
Ma'am, in the previous problem, question number 3.
question number 3.
Ma'am, first of all, you calculate Z1 and Z2. That means 2 column vector, then conjugate transpose. Then after that, Z1 into Z2 equal to 0. How?
No, I gave one. I asked I asked you to check if these two vectors are orthogonal also. I wanted you to check if the two vectors are also orthogonal. Okay, that is why.
In this case, these are actually not just orthogonal; they're orthonormal, right?
They're also orthonormal, right?
And so this matrix would be a unitary matrix.
This matrix will be unitary matrix, right?
But for this question only, I have to calculate only the 2 column vector, na? Length of the 2 column vector, na? Z1 and Z2.
Right.
1 and 1.
Correct.
According to question.
According to question, yes. Okay. You have the matrix A, and you one of the eigenvalues given to you, which is 8. So can you find the eigenvector corresponding to this eigenvalue?
Ma'am, I have small doubt.
Yes.
Why is the concept of complex matrices been there?
Sorry, why are the concept of
Complex matrices, complex numbers, and complex matrices. At what cases or what situations this will be useful?
so like you see this in rotation, like in many cases you will come across unitary matrices also, so there is one application. uh, then Hermitian matrices are also quite useful in ML part, so that is why we learn about complex matrices.
Okay, ma'am. Ma'am, if time permits, can you explain Hermitian matrix? What are the conditions?
What are the conditions? Okay. Did you do this question, solve this problem? Yeah. Okay, I see a lot of questions. I minus I by 2. I by 2. Okay. Alright, I saw a lot of answers in the chat box. So the correct one is I minus 1 minus I 2. So whoever has got 1 minus I 2, it's correct. Let's see the solution for this.
Ma'am, this answer will be also correct, no? 1 minus I by 2 and 1. Same answer, no?
1 minus I
By 2 and 1.
oh by same, that will also work. Yes.
I'm sorry, I didn't understand his question.
No, he said like I said 1 minus I comma 2 will be a solution. So what his point was like even I 1 minus I by 2 comma 1 will be a solution.
Okay. Let us see the solution.
Yeah. Okay. So if the eigenvalue is given to be 8, right? So a minus lambda I, which is 2 minus 8, which is minus 6, and 5 minus 8, which is minus 3. 3 minus 3i and 3 plus 3i. Okay. Now, if you solve this, yeah.
Sorry, the lambda 1 plus lambda 2, wouldn't it be 8
And because some of the diagonals is the sum of that concept we cannot use. The sum of eigenvectors is the sum of
No,
diagonals.
I didn't understand your point.
Ma'am, the sum of diagonals is equal to the sum of eigenvectors. No? The trace of a matrix is sum of eigenvectors.
So Subid, the other eigenvalue is what?
So we can calculate that it would come out to be -1.
Eigenvalue is given here.
It is given, no? Here, eigenvalue is given to be 8. Okay. So let's solve this. So you get, you'll have to do x1, x2. Should be 0. So you get minus 6x1 plus 3 minus 3i. x2 equals 0 and 3 plus 3i. x1 minus 3x2 equals 0.
I was doing it with echelon form. Can we do
Yeah, that will be easier. Okay. Yeah, let's do from
Yes,
echelon.
ma'am. Let us do it with echelon form.
Yeah.
This would be a comparatively difficult method.
A lot of calculation will be needed here.
Okay.
So, ma'am, I divided it by -6 to get 1. And then I proceed. Please.
Okay, so R2 should be replaced by
And why to replace? You can divide by -6, or you can directly do R2 minus 3 plus 3i into
wait, can you tell
R2
again?
by -6.
And first step, please divide it by -6. R2
Okay.
divided by -6.
Okay.
It will be easy. R1, sorry, ma'am, not R2.
So you get 1.
Yeah,
And
here,
3 minus 3i divided by -6.
so it will be directly -half plus half by I.
Right. Then you have 3 plus 3i and you have -3.
-3.
Okay. Then what do you get? Then you replace R2 with
3 plus R2 minus 3 plus 3i R1.
3i R1. Right?
Yes.
So what do you get? You get 1 minus
3i by
1 by 2 plus I by 2. Right? And this will be 0. And this will become -3 minus 3 plus 3i R1, which is 3 minus 3i by -6. Right? So -3 plus a plus b, a minus b, a square minus b square.
3 minus 3i by -6.
Right? So 9 minus 9 plus 9, 18 by 6. So -3 plus 3, which is 0. Right? So from what do you get from here? You get x1 plus I minus 1 by 2 x2 equals 0. So I can write my eigenvector as so here from here what can you do? You can do x1 equal
Ma'am, how
9.
you got 0?
Just calculation. I did
x1 will become 1 minus I by 2.
yeah.
X2 is 1, yes, ma'am.
Yeah, just this one. So it becomes 0. So we got
So that will be 9 plus 9, no?
no, this is there's 9 plus 9, which is 18. 18 divided by 6 is what?
Okay.
So you get 0. Minus 3 plus 3, which is 0.
3 minus 2.
So if you take x1, x2 to be 1, x2 can be 1 minus I by 2.
2.
Yeah. So any any scalar multiplication of this is also your eigenvector. So if you want to get rid of this by 2 sign here, so you can just write 1 minus I and 2.
I don't know what mistake I'm making. Could you just scroll up?
Okay.
And if we we do without the reduced row echelon form, and we look at equation 2 that you had written here, 3 plus 3i x1 minus 3x2 is equal to 0. Taking x1 as 1, what would we get x2 as?
You mean after this?
If we use the second equation that you've boxed here at
This
the
one?
no, in the upper slide on your left bottom
This one?
corner.
This one?
Yeah, the second one. If I take x1 as 1,
okay,
in the second one, then what do we get x2? Am I making a mistake? I'm getting 1
if
plus.
you take x1 to be 1, is it?
Yes.
Okay, then you get what? You get 3 plus 3i minus 3x2, right?
Yes.
You get x2 to be 1 plus I. You get
Yes.
x2 to be 1 plus I.
Can we do that without doing the echelon form? Can we do x1?
So I was getting 1 plus I.
I'm also getting the same answer, ma'am.
And
1
yet
plus
your answer is completely different.
What are you getting?
No,
One
ma'am.
plus I.
Okay, what is
1 plus I.
Yeah, so the answer will be same, ma'am. Answer will be same.
For giving x2 the value, I think.
Okay, first, can you tell me what answer did you get if you solve from here?
Ma'am, it is correct. 1 plus I is also correct. You can multiply it with.
No. What answer did you get?
1 plus I.
No, I think x1 we can't give it as
1 plus I.
Right.
But how,
Mistake.
ma'am?
That
Are
is
they
the
the
mistake.
same? Are they the same?
How? No.
I don't think.
No, that is the mistake.
If we multiply them with 1.
1 minus I, if you multiply it with 1 minus I, you get
yes
1 minus I square, right? Which
And
is
bottom
nothing
will
but
be
2.
0.
But x1 is not a free variable actually. We can't use straight away x1 equal to 1, no, right?
No. So there is a wrong in the first assumption. So if you go there, so x1 equal to 3x2 by 3 plus 3i. So you take the 3 common, so it will be x1 equal to x2 by 1 plus I. 1 by 1 plus I. So if you take x2 equal to 1, then x1 is 1 by 1 plus I. Then you might multiply 1 minus, then you will get the same result.
Yeah, but my point is, without doing any row echelon, how will you know which of this is the
Same things we are telling.
Yeah.
solve the equation then.
You just solve these two equations. Like, how do you generally solve the two equations?
That's what I'm saying. So unless we solve, we have to solve it without assuming either x1 or x2 as 1. That's what I'm saying.
Yes.
Sir, whatever it is, when we are doing RREF also, we keep the first one as pivot, right? So the second will be the free variable, if at all.
Yeah, that's what
When
I
the
was saying.
independent one.
No, as I think he was pointing out, who's that? I didn't get his
I
name.
am pointing out you have done a mistake. So I am saying x1 equal to, if you take the second equation, x1 equal to 3x2 by 3 plus 3i. Okay.
Yeah, you're
So
saying
here,
about substitution. Yeah, substitution. Okay.
so if you take then the x2, then if you take the x2 equal to 1, then the top variable will be 1 by 1 plus I. Now multiply the 1 minus I, you will get the result.
Okay.
I'm sorry, I don't follow. Ma'am, could you just clarify? You just multiplied both by
Multiply it
1
with 1
minus
minus
I,
I.
and you're arriving at the same solution that you got through the reduced row echelon
Yes.
form, right?
Yes.
That means that answer is also correct that I have got.
Yes, that is also correct.
Yes, that's what is any scalar multiple of this
Yes.
is going to be correct answer.
Yeah, so this answer is correct, right?
This answer is also correct.
But then in the exam, I mean, it can be
No, in the exam,
confusing.
like, and if at all comes, it will be an MCQ format, right? And in MCQ format, it will be make sure that you're like they're not scalar multiple.
Yeah, because in this it's really confusing. If I hadn't done the reduced
So
row echelon form, I
if
had
you
done it through this, I would not have been able to even identify that this
no
one
no
you
no
got
you
is
you find
correct.
you find anyone, like whatever method you use to find it,
Yeah.
you find it and then check in the options if anyone is a multiple of
No,
what you
I
got.
got you.
Yeah.
But then, like the answer you got through the reduced row
Huh.
echelon form, I
Yeah,
would
I
not
can
have been able
understand.
to
Yeah.
figure out it is the same as mine.
Yeah, so that is why to take care, like if you are getting the right, like to check the answer if it's not matching with your option,
Hmm.
just check if
There is
what
some way you
multiple
can
you
do a
got,
scalar multiply.
scalar multiple.
Okay.
Okay.
Right.
Yeah.
So, ma'am,
So,
1 plus I is also right, ma'am.
1 plus I is
so
also right.
so in that case, ma'am, we will have to multiply with all the available options and need to check if they are coming out as 0.
No.
No, what did you say?
I mean, in MCQ, if we have multiple options and more than one answers are correct, so in that case, we will have to do some kind of reverse engineering, multiply with the answers. Eigenvectors over there, and need to check whether that is satisfying that equation or not. We are getting 0 or not.
Yeah, that also can be done. Like
Okay.
that is also one way to check for eigenvectors. Yeah, if at all it comes in the exam with the
Because
options.
because I can find one vector, one eigenvector over here, one plus I, but there is another second one is also correct. So to figure that out, we'll have to do reverse engineering.
Whatever you think can be done, it's fine.
Okay.
Well, these
So
are
long as
just
you get
simple
the answer.
manipulations, right?
Yes, just simple manipulation, nothing much. Okay, let's move to the next problem. Okay, we spent a
Yes.
lot of time here. Okay, so here you have to check if the eigenvalues of this matrix will be real or complex.
Real.
Real. Why is that?
It is Hermitian matrix, I think.
It
Yes.
is Hermitian matrix, right? So whenever things like that comes, do not always go for finding out the eigenvalues, because that is difficult to do it, right? It becomes very difficult to solve for 3 cross 3 matrices. So check for if there is some pattern you can find, or some special kind of matrices there. So in this case, you see that this is a Hermitian matrices. So in case of Hermitian matrices, the eigenvalues are real. So you can directly say the eigenvalues are real in this case.
And can you explain what conditions satisfies it as Hermitian matrix?
Okay.
I
So
think that there is only one condition, right?
there is only one condition, yeah. So
Yes,
all
that equals to A.
all the eigenvalues of A are real. So
Basically, it is
let's
symmetric matrix in complex
And
form.
AJJ equals to A.
Yeah, let madam explain, please.
yeah, let me go through like whatever was done in the lecture. So first thing we had seen, the first thing is definition. Okay, so any matrix is called Hermitian if A star is A, and A star is just A transpose conjugate, correct? So that is a definition. Then the second property, like one the property of Hermitian is, if A is Hermitian, then all the eigenvalues of A will be real. Okay, this is one thing. You must also have seen the proof previously of this. So if you have a Hermitian matrix, always remember that its eigenvalue will be real. This is one property. Hmm.
And eigenvalues are always distinct in the Hermitian matrix case.
Eigenvalues are always distinct.
Is that the case?
um,
No.
Wait. Not necessary.
No, but in
No, no,
real,
it will be. It will be.
we are
It
getting
will be. It
duplicate
will
also.
be
Yes, ma'am.
because. Sorry, you will get.
Yes, but in real space we used to get eigenvalues repeated. No, yes, x
No,
vector
no.
especially.
You will get different. You will get different eigenvalues for Hermitian matrices.
Okay.
So also okay. One is if you have a Hermitian matrix, then first property is all the eigenvalues will be real. Then the proof is also given in the lecture. Right now will not look at the proof. So just remember the property. One is if it is Hermitian, eigenvalues are real. Then second thing is if you have a Hermitian matrix, then eigenvectors corresponding to different eigenvalues will be orthogonal. So if you have, let's say, a 2 cross 2 Hermitian matrix and you have two eigenvalues, two eigenvalues, lambda 1, lambda 2, and if they are not same, then you'll get two different eigenpair as in lambda 1 v1, lambda 2 v2, and those two vectors will be orthogonal. So even in the symmetric matrix case, you had seen that corresponding to different eigenvalues will get different eigenvectors. So the same hold for Hermitian matrix here. I will also write down those points somewhere. So again,
Only
the proof
because
was
the vectors are orthogonal, then we can conclude that eigenvalues are distinct. But
sorry, can you repeat? I couldn't.
only because for any Hermitian matrix the eigenvectors are orthogonal, so that we can conclude that eigenvalues are distinct.
No, I don't think
No,
that.
no, 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 no.
Is the other way it is also correct? That's why.
Other way is not. No, the other way is not correct. I mean, what I told, like if the eigenvalues are not repeated, then in that case, if A is Hermitian, you get two distinct eigenvectors, and those two eigenvectors will be orthogonal.
But if ma'am it is orthogonal, then the eigenvalues has to be distinct. Otherwise, it will give the same vector, and that will not be orthogonal. If any two, yeah.
But that does not guarantee that all the eigenvalues have to be distinct. Like for example, it's
No. I just asked if the vectors are orthogonal, then it is guaranteed that eigenvalues are distinct.
If the vectors are orthogonal,
Yeah,
or
it is
what do you
correct.
mean? What do you mean from there? Like if the vectors are orthogonal,
If the eigenvectors
eigenvalues.
for any Hermitian matrix are orthogonal, or say any
If
matrix, any complex matrix, if the vectors are orthogonal, then the eigenvalues has to be different.
Eigenvalues has to be different.
That's what my doubt.
Is it true?
Otherwise, ma'am, if the eigenvalues, if any two values are same, then the vectors will be same, and that will not be orthogonal.
yes, ma'am, it is if they have distinct values.
Hold on.
Yeah.
I think it's not related to case 2.
Yeah, but it's good to check.
It is in Hermitian matrix properties only, so it is in
Yeah.
quiz 2.
Excuse me, ma'am.
Yes.
The fact that they have, mentioned that two distinct eigenvalues, uh, uh, we can say that, there may be eigenvalues which will be same. Maybe not for 2 cross 2 matrix, but when we go like for a higher order matrices, then maybe we will end up with I think there was one question in graded. I had asked Sir too. There in that I think I was getting two eigenvalues same and one like two distinct and one same.
1 equal.
Yeah,
No,
it
no,
is no,
it
the
is not.
question is
It is not
different.
related to order of the matrix. It doesn't
Question
matter.
is different. Yeah, it is true that we can get the repeated eigenvalues. Hold on. Hold on. Okay. Just hold it for some time. I will think about it, and
Yeah,
with
yeah, it's
the
fine, ma'am. Maybe
problem
you
is getting
can check it
solved.
in the
Yeah.
end.
Yeah, I can check it at the end. Okay.
Yeah, yeah,
So we
no.
saw two properties of the Hermitian matrices here. So the first is if the matrix is Hermitian, eigenvalues should be real. All right. Second is if your matrix is Hermitian, then and your eigenvalues are non-repeat. Eigenvalues are distinct, right? Then corresponding to distinct eigenvalues will get distinct eigenvectors, and those eigenvectors will be orthogonal to each other. So for example, let's say you have a 2 cross 2 Hermitian matrix. Okay, then if I have two different eigenvalues, let's say lambda 1 lambda 2 for A, then the eigenpair like lambda 1 v1 lambda 2 v2, so v1 v2 should be orthogonal. This is what we are saying here. Then yeah, these two properties were there. So all right, so also you know that if you have n cross n matrix, right, and you get and if you have, let's say, n distinct eigenvalues for the matrix A, then you get n distinct eigenvectors, right? So and those eigenvectors will be linearly independent, right? So you can diagonalize your matrix A. Okay, so this is one thing. Let me write it over here. Let me write it over here. So the first thing is, if A is Hermitian, all the eigenvalues are real. Okay, then the second point is, if A is Hermitian, then corresponding to distinct n distinct eigenvalues, you get n eigenvectors, and they will be linearly independent. Okay, so that means it will diagonalize your matrix A. Implies A will be diagonalizable. Okay. All right. Okay. So after this,
Just a minute, I'm noting it down.
you can check in the notes. It is okay.
Yes.
Yeah. Let's see this.
So, ma'am, can you write one diagonalizable form because somehow P must what will be the form?
I will give
Diagonalizable.
you one. I will give you one question, and you can do that.
Okay, because it is sometimes become very confusing.
Okay. So the next question is the matrix A unitary diagonalizable?
It is, ma'am.
It is. Why is that?
A is Hermitian, so it is
A is Hermitian, right? So you know that if a matrix is Hermitian, it is unitary diagonalizable. So this property you have seen before. So this is
Sorry,
because
I don't understand what it means by unitarily.
uh, okay, it means you can write what does it mean is it means that you can write your A as u d u star, okay, where u is your diagonal, sorry, u is your unitary matrix.
Length of the column vector is 1, man. Then it is unitary, no?
It is unit. You can check. I mean, unitary matrix.
Hermitian and
You will
length
have
of
to
column
check.
vector is 1, I think. Yes,
No.
ma'am, it is.
Yeah,
Is
the
it?
the columns of unitary matrix will be ortho. Will be
For the
Yes. Yes.
sorry, for what you are saying is
ma'am, the columns, the length, the norm of the columns of a unitary matrix should be 1.
yes, right.
So, ma'am, I have a one doubt. So, you tell that it is a diagonalizable because it is a Hermitian matrix. Okay.
This is a Hermitian
In
matrix,
matrix.
and
Okay.
we know that Hermitian implies unitary diagonalizable.
But
Have you studied about normal matrix? No, no, right?
yes, this is
So,
orthogonal matrix. The square symmetric matrix and
okay.
orthogonal matrix we are talking about.
So this is something that you have seen in lecture. Like if your matrix is Hermitian, it is also unitary diagonalizable.
But I thought it was
In,
only diagonalizable if the
It is a
eigenvalues are distinct.
yes.
no, that in that case it is diagonalizable. But what we are saying is like looking at a matrix. Okay, if I'm giving you one matrix, like when can you say it is unitary diagonalizable? One way is of course you will check the eigenvalues, and if you have distinct eigenvalues, then it is then in that case it is diagonalizable. That is another thing. But we have also seen that like if your matrix is Hermitian, then it is unitary diagonalizable. You have seen it in the lecture. I will show you here. So
It is clearly mentioned in the lecture that if it is
yes, it is clearly
Hermitian,
mentioned in
then
the
it
lecture.
is.
Yeah. See, Hermitian matrix is unitary diagonalizable. And what exactly is unitary diagonalizable? Unitary diagonalizable is any matrix A is called unitary diagonalizable if there exists some unitary matrix such that A can be written as U lambda U star, where lambda is a diagonal matrix. Okay. So
Yes,
can you,
thank you.
yeah, for if you want to see the proof like why Hermitian matrix is unitary diagonalizable, you can check in the lecture. It is done. So okay.
So, ma'am, D is an upper triangular matrix or diagonal matrix. It is simply diagonal matrix.
What?
D. U star, where D is.
UD star, which is D is diagonal matrix.
Okay.
Okay. So for now we have said this is unitary diagonalizable. Now can you tell me how will this diagonalization look like? So can you find one U and one D such that A is U star? Can you do it?
It will take some time, ma'am.
Yeah, please
It
do
will
it.
take.
Because you will get such questions and you need to practice.
I hope we will get 2 by 2 matrix only.
We cannot guarantee that.
Yes, both will be 2 by 2.
No, I am saying in the exam.
Can you repeat, ma'am?
So diagonalizable D matrix will be eigenvectors, eigenvalues, I believe.
D will be yeah, like you find the eigenvalues and that will go to D.
D. And U will be eigenvectors. Normalized eigenvectors.
Yes.
So what we have to find in this map?
You have to find one. You have to find U, and you have to find D in this case.
Ma'am, sorry, I lost my connection. I just wanted to get clarification. We have to
The
find the eigenvalues, right?
the question is, now you have checked that this matrix is unitary diagonalizable since it is a Hermitian matrix.
Yeah.
Now you have to find this
D.
D and U.
So to find D, I need to find eigenvalues, right?
To find D, you need to find, yes, you need to find eigenvalues.
And that would be the long route that we know.
It's a 2 cross 2 matrix, so will not be so difficult.
Okay, thank you.
Yeah, yeah.
Meanwhile, can you explain the sixth one, how it is for Hermitian matrix?
Sorry.
Meanwhile, can you explain the sixth one, how it is Hermitian matrix?
Sixth one. What is in the sixth one? Okay. I suppose everybody has written the problem. Okay. So when do you call a matrix to be Hermitian? When A star comes out to be A, right? Now, uh, what is A star? A star is A bar transpose. Okay. So let's take A bar. So what is A bar? It will be 1 plus I, 3
Plus 2i.
plus 2i, 1 minus I minus 5i, 3 minus 2i minus I 0, right?
Okay.
Now you take the transpose. You take the transpose, you get 1 plus I, 3 plus 2i, 1 minus I minus 5i, 3 minus 2i minus I 0. Okay.
Okay, but
So
first part.
you see they both are same.
Yeah.
Yeah.
Okay.
And you don't really have to go through this long process. Like, in what you can check is, see, the diagonal entry will be always real. Okay, that is fine. Now you need to check that these off diagonal element. So if this is 1 minus I, take the conjugate, it should be 1 plus I, right? Then you look at 3 minus 2I, its conjugate should be 3 plus 2I.
Plus 2i, yes.
Minus I should be I. That's all. Enough.
Okay.
It's enough. You don't have to go through this long process.
Okay.
Yeah.
Well, finding the eigenvalue for complex matrix, same process like you have usual case, right?
Same process.
Characteristic equation, then find out lambda.
Yes.
Thank you.
And can we move faster because SVD is also there?
Yes. Do we have the answer for this?
I'm just about to complete, ma'am. Just a minute.
Just wait for one more minute. Okay.
Okay.
Can you mute yourself? Okay. What
Eigenvalues.
is Yeah.
Eigenvalues are 2 plus root 5 and 2 minus root 5.
Right.
And the eigenvectors for minus 2 iota by 1 plus root 5 and 1.
You got. Hold on. What is the eigenvalue? Eigenvector you got?
One eigenvector is minus 2 iota by 1 plus root 5 and 1. One column vector. And the other one should be orthogonal, so we can take it like that, no?
Okay. Let me just write the answer here. I can do it. So the eigenvalues that you get. So lambda 1 will come out to be 5 minus root 2. Sorry, 2 minus root 5. Plus root 5 and 2 minus root 5. Okay. These are the eigenvalues. And corresponding to these eigenvalues, you have the eigenvectors to be root 5 iota minus I by 2, and you have root minus I root 5 iota minus I by, sorry, just check this.
Ma'am, I got these, but for you, do we have to like divide by the norm, right?
Yes, you have to divide it by now.
Now, while dividing it by norm, then we have to consider root 5 I square. I mean 5 into minus 1, minus 5.
5 into
I square, which is minus 1, so minus 5, ma'am.
no, this is okay.
Can you please norm it, ma'am? This one only.
Okay, yeah.
But the root 5 is for, sorry, root is for both 5 and I, or only 5?
Only
It
for
is
5, ma'am.
only for 5.
Is this the normalized form, the unit form? This
And
eigenvector
can
is
you
given
please
here.
tell me the process how you get this 5i minus 5i?
After this, we'll start SVD. Okay.
Yes, ma'am.
Yeah, let's do this first. So you have 2 plus root 5. Then what do you get? You have already 1 minus lambda, 3 minus lambda, 2i minus 2i. Okay.
Yes, ma'am.
Corresponding to lambda 1, which is 2 plus root 5. Okay. You get 1 minus 2, which is minus 1. So minus 1 minus root 5. This is 2i. This is minus 2i. and 3 minus 3 minus 2, which is 1 minus root 5. Okay. Again, you can do this process of um, row reduced echelon form, and you can get, so if you do it, you will get or let's just directly solve this. So you get minus 1 minus root 5 x1 plus 2y x2 equals 0 minus 2y x1 plus 1 minus root 5 x2 equals 0. Let's divide the second equation by 2y and the first by 1 minus root 5. So minus 1 minus root 5, 1 minus root 5. Okay. x1 plus 2i 1 minus root 5 x2 equals 0, and you get minus 2i x1 plus 2i 1 minus root 5 x2 equals 0. So what do you get? This you can subtract, this is gone, and you have minus root 5 plus 1 minus root 5 minus 1 x1. This is minus 4i square, which is plus 4i square, which is minus 4 equals 0, right? So this is again uh, a plus b, a minus b. So a square minus b square. So 4x1. Something went wrong. Hmm. Okay.
Can you tell by checking the answer that the vector we are getting, that is orthonormal, or I mean to say the vector we are getting from this process is already norm 1, or it is?
No. It won't be. It will. You'll have to get it into norm 1 by dividing by its.
Yes.
Yeah.
Okay.
So just do this. Let's not spend more time here. I think I have
Yeah.
done
Okay.
some mistake
I'm
here.
just write down the answer. We'll check it afterwards.
Yes.
Ma'am, should you like eliminate x2 term as well, because we need to find x1 in terms of x2, right?
Right.
So why are we eliminating the x2 term? This will always lead to, I believe, 0, 0. Because both the equations.
Correct. Yeah. Right.
Instead, what we can do is like take the x2 term on the right side and
Right x1.
yeah, transform it in terms of x.
Yeah. Yeah. So you get x1 to be minus 2i by minus 1 minus root 5 x2. Right?
Yes, ma'am, and then you can rationalize the denominator.
Yeah. So 2i by 1 plus root 5 x2. So you can write v1 to be 1 plus root 5. Now you need to make this to norm 1. So just divide it by its norm, and then before doing that, you can rationalize also this part. So you get in the numerator part 1 minus root 5 divided by 1 minus root 5, and then get the v1 vector, and then find the unitary matrix, and then proceed.
This you calculated for which eigenvector?
This is for 2 plus root 5. 2 plus root 5.
2 plus root 5.
Yeah.
Ma'am, can you please just show me the how to normalize, ma'am, if you want to normalize the complex one, especially the 2i divided by 1 plus root 5. If
Okay.
you show that also, it's enough, ma'am.
Okay, 1 plus root 5 into 1 minus root 5, 1 minus root 5. You get 2i, 1 minus root 5, a plus b minus b, 1 minus
minus 4. Denominator is minus 4.
minus 4, right? Yeah.
Only minus 4. Yeah.
Yeah, minus 4. So you get I1 minus root 5 and minus 2. So I can take just a bit here, and this is what you get. So v1 comes out to be minus I 1 minus root 5 by 2, and it is 1. Now find what is the norm of v1. We'll just do it here. Okay. So
Ma'am, we've divided by the norm, right? But only the first element of the column vector.
no, I didn't understand. What did you say?
We divided the column vector v1, the first element, by the norm, right? To get that minus I bracket 1 minus.
No, this we just rationalize. This we just rationalized.
Oh, we rationalized or we divided by the norm?
No, we rationalized.
But we have to normalize that, right, ma'am?
Yeah, we are doing it. So once you do it, you get minus I square by 4, 1 minus root 5 square. Is 1. Okay, this will come out to be very complicated. So
yes, ma'am, I'm getting also complicated.
Yes, ma'am. Actually, this one only the norm, finding norm with I. It's really.
Yeah. Just leave this part, okay?
Okay, ma'am.
So you know the process.
This is complex, ma'am.
This
really,
is
really
yeah,
complex.
this is really complex. Yeah, just leave this.
Actually, my question is, ma'am, now we got minus I square, no? So can we convert this into plus 1?
Yes.
Okay.
Yeah.
Okay, ma'am.
Okay. So you know the process. You can just do it. So there is just one more question I'd put in. I'll share the slide, and maybe you can write yourself. So this is for the shoes.
Just for one clarification, had we been able to normalize v1, that would be just
one
column vector of the u, right?
Yes.
And then we would have to do
Do
have
for
to
the
find
other one.
v2 also with the different eigenvalue,
Right.
and then again normalize it.
Correct.
Okay, thank you.
Yeah. Okay. Let's move to SPD. Oh, there is no more question. Yeah. So maybe we can do just SPD today, and tomorrow we can do positive definite matrix.
Let me just write the question previous one.
Yeah, I will share the slide so you can take it from there.
And can you write the answer also if you have already?
I will write it and upload.
So, ma'am, what is the concept you are using for the T? Is it also with eigenvalues? No.
Yeah, again it's eigenvalue. So here you have to use the Schur's theorem, right? You have studied Schur's theorem. So what does it say? Schur's theorem. Any matrix, any is there? Yeah.
It is the same, man. Any Hermitian matrix is a unitary diagonal.
But it is not a
Any
Hermitian matrix. It is not Hermitian matrix.
no. Schur's theorem says that if you have any n cross n matrix, then you can upper triangleize it. So upper triangleize means like you used to do this UD transpose, right? So when we say it is unitary diagonalizable, we say it is of the form UD star. But now if we say instead of D, it should be an upper triangular matrix, and there is a way you do it. So just repeat the process that has been done in the class. You will get the answer.
So, ma'am, could you please explain, like, at least and mention the steps that we can follow for shoes?
Yes. So you have the matrix, right? And we say that you can write that matrix in the form of U star, right? And this U is unitary matrix, okay? And this T should be your upper triangular matrix, okay? So like what do you do for in case you have to find D? So you
Eigenvalues.
first find the eigenvalues, right? So you find the eigenvalues and put it. Just give me a minute. Okay. So you find the eigenvalues, then you find the eigenvectors, and since you need the unitary matrix, right? You need to find, you need to check if the matrix is unitary also. You find the corresponding eigenvectors for that. You will find your U. You will find, and D you will find from. Sorry, we're talking about triangular matrix, right?
Yes, ma'am.
Yeah. Can I put this example is given? Okay, I will give you the step-by-step process for this question. Okay, I will write it down and put it in the slide.
Okay.
Yeah.
Ma'am, to check for unitary matrix, either the matrix magnitude should be 1 or it is. There are two
Sorry.
properties. It should be orthonormal or it should be only orthogonal, ma'am.
Unitary matrix, it should be orthonormal. The vector should be orthonormal, like the dot product should be 0 and the length of the
The
vector should
length
be 1.
magnitude is 1. Okay, ma'am.
Yeah. Okay. Now let's come back to SVD. So what we have seen in SVD, like we have look at the diagonalizable part only for the symmetric matrices, and we had decomposed. We had seen the decomposition of those matrices. But what happens if your matrix is not diagonalizable? So what do you mean by not diagonalizable? Uh, so if the matrix is not if the matrix is not symmetric, then in that case also it is possible for you to write it somehow in the form of some u sigma v transpose, okay, where u and v are orthogonal and sigma is a diagonal matrix. So this diagonal matrix, I will just go through what the notations in the lecture you have used. So we say even if the matrix is, let's say, some rectangular matrix m cross n, even those matrices can be decomposed in the form of some q1 sigma q2 transpose, where q1 and q2 are diagonal, q1 q2 are orthogonal matrix. So q1 q2 are orthogonal, and the sigma is your diagonal matrix. So how do you, like, what are the steps you follow to find the diagonal, to find the SPD of a matrix? So the first thing you do is you find, I will just write the steps. Okay. So the first thing is your matrix is m cross n, and you're writing it in q1 sigma q2 transpose, correct? So any q1, this is going to be m cross m, this is m cross n, and this should be n cross n. Now the first step is you find the eigenvalues and the eigenvectors for A transpose A. This should be your first step. Okay. So first you have A given to you. You find A star, A transpose A, and find the eigenvalues and the eigenvectors. Find lambdas, find Vi. Okay. Now take these pairs, take these eigenpairs, and use this to VIs to find your matrix Q2. Use this to find your matrix Q2. So Q2 that you write is nothing but, let's say, if the eigenvectors for A transpose A comes out to be eigenvectors comes out to be x1, x2, and so on. So you will use this, there will be n. So you will use this to get x1, x2 to xn. And it's not just these xi's, you need to normalize this. Okay. So you normalize this and find the orthonormal vectors. Find the orthonormal vectors and just put it in Q2. This should be your first step. So you already found the Q2. Now to find the Q1, you need to find the Q1. So to find the Q1, you use the process sigma I yi equal axi to get yi. Okay.
Ma'am, can you please tell the matrix Q2 with the example, ma'am? Because already we have vectors in column wise. Then again we have to write it in column wise, ma'am. Q2.
We'll look at one example.
Okay, ma'am. Thank you.
We'll look at one example. So, okay. Q2, yeah, Q2 we have written. Now, in order to find the Q1, we do sigma I yi to be a xi. The proofs and all you have seen it before and in the lecture. So just look at the process. So sigma I yi equal a xi to get your yi. All right. So whatever yi, and what is the sigma I? Sigma i's are under root of lambda I. All right. So use from there you find your y. So you find your y. So you get q1 to be some y1, y2 to some y. Okay. Now you have your q1, you have your q2, and your sigma. So the sigma is left here, right? So what is the sigma that you get? Sigma should be so corresponding to this x1, what is the eigenvalue you had? So just write the under root of that eigenvalue, then under root of this eigenvalue. Okay, it will go on till depending on if your number of rows are greater or which one is greater. Okay, and you will get something of this form. This will be your sigma.
Also, ma'am, do the eigenvalues have to be like in order, like in?
Yes. I mean, you put the eigenvalues in the decreasing order. So if you're, let's say, x1 is For corresponding to lambda 1, you're getting x1. Just put, just let it be in order. I think it doesn't matter. So corresponding to lambda 1, you have x1. Just write it in order. So the way you write it for u, d, u star, right? I mean, corresponding to this d, you find, you have the eigenvector in u.
Yeah,
Just maintain that.
but like some order has to be there because like
Si-
the two
yes.
orthogonal matrices are of different size, right?
So the order is like we put uh, sigma 1, the greatest one, to be on the top. Then you put sigma 2.
Got it.
Yeah, something like this.
Ma'am, here I have a doubt.
Yeah.
So, sorry. So sigma will be of the dimension m plus 1, is it?
Sigma is, I mean,
Because we have the lambda spanning from 1 to m. So I was having confusion with the 0, which is written down. So
sigma is m cross n. Sigma is your m cross n matrix.
okay, good. So the remaining, you can say n minus m will be zeros, right?
Remaining m minus, yes, it will be 0.
Thank you, thank you.
Yeah. Okay. So these are the steps that we follow to find the SPD of a matrix. So one thing here, I have told it before also. So since A is Q1 sigma Q2 transpose, you can check that this A transpose A gives you Q2 sigma transpose sigma Q2 transpose, and AA transpose will give you Q1 sigma transpose Q1 transpose. So because we are able to write, this A transpose A and A transpose, they are symmetric matrices. So we are able to write this symmetric matrix in this form. So it means they are, we are able to diagonalize it.
One doubt, ma'am. When we talk about the eigenvalues, we keep it in ascending order. Like we get eigenvalue 1, 4, 3, 1, 4, 7. Then we will write lambda 1 is equal to 1, and lambda 2 is equal to 4, and lambda 3 is equal to 7.
Lambda, okay, 1, 4, 7. Is it that what you said?
Yes, ma'am. Then lambda 1 for 7 is lambda 1 is equal to 1. When we get like any value like 1, 4, 7, 1, 2, 3 or anything, we will arrange them in ascending order now. Like lambda 1 is equal to 1 and lambda 2 is equal to greater than 1.
I mean, in both ways you can arrange. I mean, you can arrange either in ascending or in descending, but just put it in order. Either you write 7, 4, 1 or you write 1, 4, 7. It should be in order, whatever eigenvalues are getting. Okay. So if you are maintaining the ascending order, maintain that. If you are writing in descending order, just maintain that. Okay. Okay. Let's look at one question. So you have the matrix A. You have to find the SVD of A here.
Here I have a question. I think it's either a practice question or something like when we are talking about the eigenvalues, which actually will form the diagonal matrix in the HVD, right? So yes, ma'am. But for checking up, because as I was saying that please check up when it will become equal to A after you do the Q lambda Q transpose. So minus
Wait.
3 and 2. If you only give in the descending order, it's giving the correct answer. If we give it as
I did not get what you said. Oh, which practice assignment?
Actually, it's in the notes. Let me check which practice. One second. Just give me a minute.
Okay.
Well, I think it's more from the the video rather than the practice questions. I'm not too sure, but the bottom line is like the eigenvalues were -3 and 2, man. And so
Wait. So I think the test video. No? Okay. So
I'll just try to pull out my one second.
yeah, I think I know. Is this the question you're talking about? So equal root 2 1 0 root 2.
Actually, the original matrix, the A, that is uh, symmetric matrix is 1 minus 2 minus 2 minus 2.
Oh, sorry, 1 minus 2?
1 minus 2 minus 2 minus 2. That is a 2 by 2 matrix with 1 minus 2 first row and second row minus 2 minus 2.
1 minus 2?
Minus 2 minus 2. Yeah.
What about this?
So here what we were doing the SVD, I was doing the SVD for this. So I got Q1 as
okay, let's yeah, let's do this. Let me take one fresh page.
We are getting your voice, ma'am.
Oh, sorry, I was on mute. Yeah. So 1 minus 2. What was that?
minus 2 and minus 2.
Minus 2 minus 2.
Yes, ma'am.
Okay.
So
Okay.
this is
So first step is okay. First step is you need to find A transpose A. A transpose A. So what should it be? So 1 minus 2 minus 2 minus 2.
Yes, same.
Right? And A is 1 same. It is same. So okay. What do you get? 1 plus 4, which is 5. minus 2 plus 4, 4 which is 2, then minus 2 plus 4 which is again 2, and 4 plus 4 which is 8, right? This is what you get A transpose A.
Yes.
Actually,
Yes, ma'am.
actually, I proceeded with first finding the eigenvalues, ma'am, actually, because that becomes the
Yeah,
sort of.
I mean, you find the eigenvalues. This is the first step. I will go step by step, okay?
Okay.
So
Okay, ma'am, please.
step 1 you find A transpose A. So is this all of you got this as A transpose A?
Yes, ma'am.
Okay. Then next we find the eigenvalue for this. So you have 5 minus lambda, 8 minus lambda, 2, 2. Okay. So what do you get from there? You have 5 minus lambda, 8 minus lambda, minus 4. Right? So from here you get A540 minus 5 minus 8 minus 13 lambda plus lambda square minus 4 equals 0. Right? You have lambda square minus 13 lambda plus 36 equals 0. Let's solve this. So you have
I'm
1.
sorry to interrupt. We're doing a different question than the one you had given in the slide, right?
Yeah, I'm going with first the simpler one.
Okay.
Let's do it step by step. So is this characteristic is this a characteristic question you got?
Yes.
Yes, ma'am.
So minus 13 plus
9.
It is not perfectly factorizable.
9 and 4.
Lambda is 9 and 4.
9 and 4 we can do.
Yeah,
Yeah,
9 and 4. Yeah. So lambda 1 equal 4 and 9. Yeah. Okay. So you got the eigenvalues to be 4 and 9. Now we need to proceed with eigenvectors. Okay. So you have 5 minus 4, which is corresponding to lambda 1 equal 4. 5 minus 4, which is 1, which is this is 2. 8 minus 4 is 4. X1, X2 equals 0. So what do you
Ma'am,
get?
it's 1, not 4, ma'am. 1, 2, 2.
Sorry?
That's so 1, ma'am, not 4. A1, ma'am.
You have written 4, ma'am. That will be
5
1.
minus 4, 1. First row of column.
No, which one you're talking
A1,
about?
ma'am. A1, ma'am is 1, ma'am.
What is A1?
5 minus lambda. Lambda is 4. 5 minus 4 is.
Okay. Sorry. So you get x1 plus 2x2 equals 0, right? So from there you can write your v1 to be, you put x1 to be x2 to be 1, you get x1 to be minus 2, right? Now you need to make it to the norm 1. So what is the square root? It is 1 plus 4, this is root 5. So this is going to be minus 2 by root 5, 1 by root 5. Okay. Now find it for, is this right? All of you got the same answer? For lambda 1?
Yes, ma'am.
Okay. Now for lambda 2 equal 9, for lambda 2 equal 9, you have 5 minus 9, which is minus 4. This is 2. This is 2. 5, 8 minus 9, which is 1. Right? You have x1, x2. So from here you get minus 2x1 plus 2x2 plus x2 equals 0. So from there you can get right. Now what is the length? It is 1 by 4 plus 1, which is 5 by 4. So 5 root 5 by 2.
2x1 minus x2 it is, no?
It is mine.
In the equation, what you have written.
Minus 2x1 plus 2x2, which is minus 2x1 plus x2. So 2x1 should be x2.
Yeah, okay.
Right?
I got eigenvector as 1, 2 for this lambda. Is it right? X1 is equal to 1 and x2 is equal to 2.
Sorry, yeah, it is right. Okay. So this is just divided by root 5. So you get 1 by root 5, 2 by root 5. So our first step is done. Correct? Now what do we do after this? We write our Q2 matrix. Our Q2 matrix is done. So our Q2 matrix is, this is corresponding to the eigenvalue lambda equal 4. So minus
Ma'am, we have to
2 by,
write in decreasing order, no ma'am, the lambda value according. I mean,
it is all right. I mean, you can write it in increasing, you can write it in decreasing order. It's fine.
okay, ma'am.
1 by root 5, 2 by root 5. All right. Okay, Q2 is done. Now we need to find what is the step 2.
A transpose.
Find sigma.
Step 2 is you need to find your Q1 matrix. And how do you find it? You do sigma 1 y1 equal ax1 and sigma 2 y2 equal ax2. Okay. Now what is sigma 1? So let's write sigma 1 to be so lambda 1 equal 4, lambda 2 equal 9. So this is 2 and sigma 2, let's try to be 3. All right. Now what is y1? Can you find y1?
How to find
Then
it,
this
ma'am?
A should be the original A that we started with.
Yes. This is your A. I am writing your, I will write the A here. This is your A.
And x was the eigenvector.
X1 is the eigenvector corresponding to the eigenvalue lambda 1 equal 4. And that was minus to 1.
That will be unit eigenvector, or yes?
Yeah. Can you find y1?
Yeah.
Ma'am, we have to multiply both and divide by sigma 1, ma'am.
Yes.
Okay. Because in this step only, I'm always doing wrong. So if you do it and show, it's really very, very helpful.
Please try. Please try.
Okay, I will try, ma'am.
First try. Yeah.
Okay.
minus 4 by root 5
Okay, what is y1?
and 2 by root 5.
Ma'am, minus 2 by root 5 minus 3 by
Yeah,
root
yeah. Minus 2 by root 5 and
minus 3 by root 5, is it? Is this what you are getting?
1 by root 5, ma'am.
No,
Not 3.
minus 3 by root 5.
Okay,
I'm getting only 1 by root 5.
Yeah, 1 by root.
Okay. Let's check then.
Minus 4 by root 5.
Y1 will be 1 by 2. 1 minus 2 minus 2 minus 2. Root 5, let's take it here. Minus 2, 1. So this is 1 by 2 root 5. This will be 1 minus 2 minus 2, which is minus 4. And okay. And 4 minus 2, which is 2. So you get minus 2 by root 5 and 1 by root 5. This is not correct. This is 1 by root 5. Okay. Can you tell me also what is y2?
Ma'am, minus 5 by 3 root 5 and minus 2 by root 5. Is it correct, ma'am?
I don't know. What did you say?
Minus 5 by 3 root 5 and minus 2 by root 5.
I don't know. Others can maybe let other people also answer. Then I will check.
No, I got minus 1 by root 5 minus 2 by root 5.
Yeah, minus 1 by root 5 and minus 2 by root
Minus 1 by root 5 and minus 2 by root 5.
Okay. This is not right. Okay, you can check. So now we have got our y1 and y2. So you can write your q1. So what is your q1? Q1 is y1, y2. So
Ma'am,
this
is y2 values are right, ma'am?
is y2. Since most of you got it, I thought it should be right. Okay, if you want, I can check. So y2 should be 1 by 3 root 5. 1 minus 2 minus 2 minus 2. This is 1 root 2. It looks right to me.
Okay, right, ma'am. I did mistake. Okay. I got it now. I rectified it, ma'am.
Okay. So, fine. Now you have Q1 also with you. So Q1 is y1 by 2. So you have minus 2 root 5, 1 by root 5, minus 1 by root 5 and minus 2 by root 5. Alright. So this is a Q1 you got. So we have the Q1, Q2 we had found, right? This is Q2, this is Q1, and what is the sigma?
Ma'am, 2
Sigma is 2003. Now you can just cross check that your 1 minus 2 minus 2 minus 2 is same as minus 2 minus 1, 1 minus 2, 2003, and Q1 was minus 2, 1, 1, 2. Minus 2, 1, 1, 2. Just check. Can you check this? Check the product.
Do we need to do all this lengthy process in the quiz?
Yes, you'll have to do this process.
Could you show what is Q2?
Q2 is
Ma'am,
Q2
it
is
should be
this.
1/5. Shouldn't it should be 1/5, right? Because you're taking 1/√5 from both the matrices.
Oh, okay, yeah, thank you. This is 1/5.
Sorry, could you show me Q2, please?
Q2 is this.
-2.
This.
Okay. Thank you.
Yeah. Just check. Just check for this.
Ma'am, first you solve Q2, then Q1, then can you please explain sigma? How can we get?
Right.
Sir, how calculate sigma? Can you please explain once again?
Sigma, you just put it in the order. Like minus to 1 was the eigenvector for corresponding to the eigenvalue 4. So if it was the, you're putting it in the first position, this is your first eigenvector. And for 3, this like corresponding to the eigenvalue 9, this is your eigenvector.
Why we are taking sigma for corresponding to A transpose A only under root of, because we are finding first lambda for A transpose A only. Because it is symmetric, right?
It is a symmetric matrix.
And A transpose, that will be also symmetric.
A transpose will also be symmetric, right?
Why this differentiation, like we are calculating say Q2 first and actually I did this mechanically, but I didn't get the grasp of the concept why we are doing this way.
Okay, so like
there is a factor coming out to be this sigma y. We are calculating sigma 1 y1 is equal to ax1. So here it is. I can.
Like I think in the last class also we had checked this, and we had gotten this to be coming to be same if you do both cases. Like last class, this is the symmetric case. If you do for the rectangular matrix, we got this to be the same eigenvalues. I think I showed it in the last class.
Ma'am, in the exam, what will they ask to calculate, like among this Q1, Q2, and sigma?
Anything can be asked. I mean, it is not fixed. So one thing I wanted to check before I go. So proceed. How many of you have watched the tutorials for week 6?
I really don't remember him, but
Ma'am, it was confusing, but most of it was confusing.
yeah, I have watched.
Okay, you have watched.
Yes.
So there, something we are talking about. Like there is a different way to write
I mean,
your
which
SPD
tutorial?
form.
6.2.
Tutorial. I think it
There
is
are
6.1. I think it is 6.1.
real world applications. Okay, so
Yes.
There are a lot of many ways, but really it is confusing them after finding eigenvectors. Now it is okay. We will follow this method for all the matrix, no ma'am?
We'll follow this method for all the matrices. Yes.
Ma'am, we have to find either one, A transpose A or A transpose. Any one.
Any one. Right. Like as long as it is symmetric, it does not make a lot of problem. But in case of a rectangular matrix,
Okay.
you need to take care of like where, like which one, like how do you proceed.
So
Okay.
in this case,
So
it was possible to use A transpose A or A transpose, right?
yes, you can check, like even with the A transpose, you'll get the same eigenvalue.
But the one in the slide, that in that one we can't do this, right?
Uh, the
In
one
the
It
in
has
question
to be
you have asked, ma'am.
where there's a
okay,
single column matrix.
Yeah,
yeah,
that is tricky question, ma'am.
In
Please
that one we
explain.
can't do A transpose A because it just gives a scalar value.
No, that is
it gives a scalar value.
You can
single
Yes,
unit.
ma'am, it's
you
9.
just have one eigenvalue.
You just have one eigenvalue there.
The rest of the columns are just zero.
Uh,
So what would be the eigenvalue, the answer of A transpose A?
Yeah. So like it for I think it comes out as 9. So the eigenvalue is 9. And this
9, then
right.
how do we proceed to eigenvectors, ma'am? Then from which
You
matrix will...
find the
Eigenvector is 0.
eigenvector.
so the eigenvector
0.
Eigenvector,
corresponding.
it will not come to 0.
Because the value is 9.
Yeah, so
That means
eigenvector is 1. Just 1.
Eigenvector is just 1.
So and you can find the corresponding y and
Okay,
just
eigenvector, yes.
and just fill up the rest
1.
of the matrix with 0.
Eigenvector is 1.
Yeah,
Yes, yes. Only one element.
because the matrix is just 9. So the
No, it's just one element, that is the single unit digit 1, or it's just a one,
it's like
it's
a
not really.
it's like a vector, but it's just one, like a 1 cross 1
It's
matrix.
part of it's in R, right? Instead of
Yeah,
R to
yeah.
Rn. So it's in R. Would it be possible to just
so the
quickly solve
y
the
should
question?
be
It would
Yeah.
make things
minus
a
2
little
by 9.
clearer.
Yes, ma'am, if you find vectors, ma'am, then the y value should be minus 2 by 9, 1 by 9, 2 by 9.
Y value should be okay.
Because the vector value is 1. When we normalize also it is 1. So ax divided by the sigma, root, 3. Okay.
In fact,
So
if it
minus
doesn't take
2
time,
by
could you
3.
solve that particular question? I'm a little
Yeah,
confused.
I want to just give you some time to just think
Okay.
about it. Yeah, I wanted to ask, like if we this part just a little more, if we can take tomorrow, is it okay?
Yes, ma'am.
Maybe
Fine.
starting half an hour, we'll
Yes, ma'am.
spend on
Uh,
SVD a little more.
yeah, yes, ma'am. And
Yeah.
start from this question only. What
Uh,
you
wo- I want to give you some time. Just think about that question and try to
Now, if you have
see.
answer, can you please
Yeah.
write it?
Could you please share the answer so that we can?
Okay, I will share it in the chat box. Okay.
Or else you can fill the sheet, previous
Okay,
ones
I
also,
will. I
and
will write in the sheet.
Just
Ma'am,
put the answer and we'll do it
Sigma
later.
Just half an hour tomorrow I will take, and then we'll proceed with week 7 week 8. Week 8 there is nothing,
Yeah.
not a lot is there, so that is why it is okay.
ma'am, sigma
So the
value.
answer that you will get, I will write the answer. Just
Yeah.
think about it. Okay. I close the session for today. So you will get your if A is written as Q2. Do you have the question?
Yes, ma'am.
Just take a
Minus 2.
screenshot of this. Okay.
A is equal to minus 2, 1,
The
2.
question is A equal
Minus 2, 1, 2.
minus 2,
Column
1, 2.
X.
Okay. And the answer that you should get is, if you're writing A in the form of Q1 sigma Q2 transpose, then your Q1 here is, it should be minus 2 by 3, 1 by
3,
3,
2 by
2 by 3,
Okay, ma'am.
0, 2 by root 5, minus 1 by root 5, and 5 by root 45, minus 1 by root 5, 4 by root 45. Sigma that you get is 300. and Q2 is just 1. So this is the answer that you should get. Just think about it. And one more thing, like look at the tutorial once. So tomorrow we can discuss these two things.
Also, ma'am, please check my doubt also, so that we
Yes,
can
your
discuss.
doubt was the other way around, yeah?
Yeah.
Hermitian matrix property.
What
Ma'am, to
exactly was the question?
decompose any matrix, I mean, like with theorem spectrum or a SUR, then we have to, is the condition that the matrix should be symmetric?
The matrix should be normal. I am not sure if you have read about the normal matrices. So Hermitian implies, I mean, normal implies Hermitian also. So if normal also implies symmetric also.
That's
So
what.
not a problem. So if your matrix is normal, you say that it is diagonalizable, unitary diagonalizable.
Okay, okay.
And what is normal matrix? Normal is A star should be A star A. So there are many conditions that follows that are equivalent and they are if and only if. So let's not go into normal. Hermitian implies unitary diagonalizable.
Would it be possible if tomorrow you could also do that upper triangular one also, please?
Okay. But I would say just see all these things once before you come tomorrow. Okay?
Sure.
So that it is faster.
No problem.
Yeah. Okay then. I will share the recording and the slides with you tomorrow morning.
Yes, ma'am.
Thank
Thanks.
you.
Okay, thank you,
Yeah.
ma'am.
Thank you all.
Thank you.
I will meet tomorrow.
Thanks.
Yeah.
Ma'am, please write the answers also in the sheet what you have committed.
Yes.
For UT, U transpose.
Right. Yeah.
For that. Yeah.
Okay.
Thank you. Thank you, ma'am.
Thank
Good
you.
night.
Bye.
Thanks,
Good night.
thanks a lot, ma'am. Thanks for the
Yeah.
session.